the mathematical preliminaries, we started with ordinary differential equations. And then derivatives of vectors. And then we're doing product rule for vectors. And then chain rule for vectors. So done, done. So now we're on the product rule. For scalars, let's say we have a scalar, well, say we're taking the derivative of scalar u times the scalar v. That's du dt times v plus u times dv dt. Or you can write that as u dot v plus u v dot. And the basic idea is going to be the same for vectors. Just remember that there are two ways to multiply vectors. First is dot product. So if you're taking the derivative of the vector u dotted with the vector v, that's equal to the vector u dot dotted with the vector v plus the vector u dotted with the vector v dot. And then the cross product is just like you would hope it would be. So if you're taking the derivative of the vector u crossed with v, that's equal to u dot crossed with v plus u crossed with v dot. The thing to notice here is that for cross product, the order matters. So don't think of it this way. You know, for a scalar, I mean, for scalars, this is also true. If you have u times v, and you're taking the time derivative of all of it, that's just another way of writing ddt of the stuff in parentheses. You can think of that as u dot v plus v dot u, right? That's true for scalars and true for dot products because order doesn't matter. But that would give you the wrong thing for cross product. So keep the order the same, and then you'll be fine in all of those. Any questions about that? If you what? And then just use the -1 to.
No, I'm just saying wrong. So you know when you do cross product, you do one before the other.
Yeah.
Typically you'll get a negative.
Yeah. Well, it would mess it all up, not just the sign, because half of it would be the right sign and half, one term would be the right sign and one would be the wrong sign. So it wouldn't have any relation to the right answer. Any other questions?
So we can still do the dot product for each individual set the way we want, but or like the way we're used to for doing cross product, because like some of us with the term when it's a three-dimensional cross product, like what I typically do is I'll do it the way I normally do it and multiply that term only by -1, but as long as we keep U cross V and then or like the derivative of U cross V plus U cross the derivative of V, as long as we keep that order right, we'll be okay.
U plus the derivative of.
As long as we keep that order correct.
Yeah, just keep the U on the left and the V on the right, and it'll work. And you'll be doing a ton of cross products, so you probably don't want to be doing them by hand. You want to have a program that does it coming up pretty soon. Any other questions?
Oh, you don't want to see your work?
Not on the cross product, no. Just plug it into your calculator. No. I don't want to look at it either. Yeah, exactly. Yeah, that's a funny idea. Okay. And now chain rule. I'm going to give you the chain rule for total derivatives where there's only one independent variable, because that's all we're going to use. Okay, so for a scalar, the chain rule says if you take the derivative of a function f of g, and that's the derivative of f with respect to g times the derivative of g with respect to t. And you can always remember that because it looks like these just cancel out and give you the thing back that you want. For a vector, so what if this function f is a vector, d dt of the vector function f, which is a function of g, which is a function of t, works the same way. So you have the derivative of the vector function f with respect to g times dg dt. One way that we're going to use this a lot So one way this will arise in dynamics we know that the acceleration is the time derivative of the velocity. But what if, So, velocity always changes with time, but that doesn't mean that you know what the functional relationship is between velocity and time. What if the relationship is velocity as a function of some kind of position variable? That actually comes up pretty often. It's not that it's not a function of time, we just don't know what that function is, but we do know what the velocity is as the position varies. So how would you calculate the acceleration? And calculating the acceleration is super important because that's how you get it. That's how you relate kinematics to forces through Newton's second law. Well, you can't just say acceleration is equal to v prime. That's not true. Acceleration isn't the derivative of v with respect to x. It's the derivative of v with respect to t. But actually, let's write these as vectors. So v is a vector function. Okay, so the acceleration is equal to dv dt. And using the chain rule, dv dt is equal to dv dx times dx dt. And that's dv dx, which we can calculate because we know that relationship, times, in this case, the v component, the x component of the velocity. And we know all this. So I'll do an example. Yeah. Works with angular quantities too. If the angular velocity is given as a function of, say, some angular position, the angular acceleration is d dt of the angular velocity, which is d omega d theta times d theta dt, and that's equal to d omega d theta times, some component of the angular velocity, and we know all that. So when we start doing problems like that, I'll give you plenty of examples and stuff. I guess let's just stop there for now. Any questions about chain rule? So now we're done with the math. Now we can finally get into dynamics. So we're going to start with particle kinematics. Remember what kinematics means? Not necessarily, and it is related to the motion, but kind of all dynamics is related to motion in some way. The thing with kinematics is you can think of it as all you're doing is describing the motion. You're just dealing with quantities that you could take off of a careful video of what's happening. So there's no forces, no couples, no masses. It's just relationships between positions and velocities and accelerations. So just describing motion. No loads, masses, stuff like that. Yes.
Are you collecting the homework this semester, or just?
No, just put it in the binder, and then the only time I'll look at it is the 2 times I collect the binders. That way? Yeah, basically, yeah. That's true. That's a good policy. Yeah, that's true. I'll return it on Hopper or something, Brad. Okay, kinematics. What is? Okay, and what's a particle?
Very small. Something.
Okay, so that's on the right track, but it doesn't have to be. It's so it has mass. The key is that you're treating it as acting at a single location. You know, like when people do orbital mechanics, for the most part, they represent planets as particles. So it's not. It doesn't really have to be small. When you do that, you're treating it as having no length dimension. So you're treating it as having no size. But if you can treat planets as particles, it makes you wonder why you can't treat anything as a particle. The thing is, when you treat something as a particle, you lose all information about orientation. You know, if the front and back of an object are both the same point, there's no distinction between whether it's facing this way or facing this way. Okay, so it still has a location. You can still differentiate between here and here, but you can't differentiate between this and this. So therefore, have no orientation. In some calculations, you don't care about the orientation, like in orbital celestial mechanics. You know, for the most part, you just want to know where the center of the planet is. You don't care how, you know, what the spot is facing or whatever. But in other engineering problems or whatever, you know, like if you make a bridge that a car gets across, but when it gets to the other side, it's on its roof, then that's, you know, going to go over really badly.
Aren't there some fields that actually would want that, like for stunts?
Well, you'd want to know that it was going to land on its roof in that case. So yes, orientation is important in that. Okay, so the basic ideas here are that the velocity vector is the time derivative of the position vector. Remember not to make the mistake of just thinking it's the derivative of the position vector. It has to be with respect to time. And the acceleration vector is the time derivative of the velocity vector, or the second derivative of the position vector. And so you can go back and forth between these using derivatives and integrals. If you're going in the direction from position to velocity or velocity to acceleration, having a function of time is all you need. Just take the derivatives. But if you're going in the direction from acceleration to velocity or velocity to position, having a function of time for one of those is not enough. You also need constants of integration because, I'm going to write it as you need boundary conditions because you're going to be solving this using separation of variables. It's a differential equation. So, for example, if you're given that the velocity as a function of time is 2t negative t, so this is a 2D problem, and you want to calculate the acceleration function and the position function. Calculating the acceleration is no problem. We have enough. It's just a derivative. But calculating the position requires another, it requires a boundary condition. Let's say that let's say that at time equals 2 seconds, position vector is 50 meters. Okay, so for part A, the acceleration function is take the time derivatives and you just get 2 negative 1 and you're done. For part B, we have that the velocity is this function. We want to figure out the position, so we're going to represent the velocity as the time derivative of the position. So I'm going to write this as px dot is equal to 2t, where the position when time is equal to 2 is equal to 5, and py dot is equal to negative t, where at time equals 2, the y position, this is px, this is py, is equal to 0. Any questions about that setup? And so then I'll just solve the first one first. This is an uncoupled system. All the x stuff is staying in the x equation. All the y stuff is staying in the y equation. So we have that dpx dt is equal to 2t. So dpx is equal to 2t dt, integrate. So px is equal to t squared plus c1. Then the boundary condition says 5 is equal to 2 squared plus c1. So c1 is equal to 1. So the position function is t squared plus 1. Any questions about that? And then same thing for the y component. We have dpy dt is equal to negative t. So dpy is equal to negative t dt. Integrate. And you get py is equal to negative t squared over 2 plus c2. The boundary condition says when time is equal to 2, py is equal to 0. So 0 is equal to negative 2 squared over 2 plus c2. So c2 is equal to 2. And so the y position as a function of time is negative t squared over 2 plus 2. Any questions about that?
Would we write that in vector form when we're done?
If you did it like that, that's fine with me. But yes, then you could combine these two and use reach. So you could say the position vector is t squared plus 1 negative t squared over 2 plus 2. Either of those is fine with me. I think this is something that you have to do in the homework problems, but the equations that you used probably pretty often in physics 1 are for constant acceleration. And I'm not going to go through all of these, but to derive the constant acceleration equations, you start with the acceleration as a function of time equal to just constants. And then from there, you integrate to get the, find the velocity as a function of time. Given that at time equals 0, the velocity vector is equal to, v0x, v0y, or whatever you want to call that initial velocity. And so like for the x component, you would say vx dot, that's the acceleration in the x direction, is equal to this constant ax. Where the velocity, the x velocity at time equals 0 is equal to this constant v0x. Then you use separation of variables. So Vx is equal to AXT plus a constant. The boundary condition says when time is equal to 0, Vx is equal to V0x. So this constant V0x is equal to AX times 0 plus C1. So that C1 is equal to V0x. And so as a function of time, the x velocity is, I'm going to just reorder the terms so it's in the form that you see most often, but it's equal to V0 plus AT. Okay, and you could integrate again, use separation of variables again to derive the position function for constant acceleration. Okay, so now really the only other thing that we have to do is these problems where you don't have the kinematic functions explicitly written as a function of time. Okay, so that was that chain rule thing that I was talking about. So let's say we're trying to go from velocity to acceleration. When the velocity is not explicitly a function of time. This is actually something that you would have to do pretty often because acceleration is the only, you know, like when you're downtown and you're like on the 7th floor of some building and you're like, I have to get over to the 7th floor of that other building, but still I have to go down to the 2nd floor to get onto the skyway. The acceleration is the only skyway between kinematics and kinetics, you know? So if you have the velocity and you want to get to kinetics, even if you want to do your kinetics as a function of position or x or whatever, still somehow you have to go from velocity to acceleration to get over. Okay, so for example, let's say that the velocity is given as 5x x squared. And what we're talking about here is that x is, you know, the x component of the position vector. And we want to calculate the acceleration as a function of x. Well, the approach we're going to use is that dv dt, you know, that's what the acceleration, that's the definition of the acceleration. We can express as dv dx times dx dt. Yep. There's no way we could get that, but what we could, if we know something about the path that the object's on, a lot of times it's useful just to be able to figure out the acceleration at whatever location you're at. And so there's no way we could get the other thing, but this is still useful in a lot of cases. But the problem is that if velocity is written as a function of x, you can't just take the derivative and be done like you could if it was written as a function of time. So we use this chain rule thing that says the acceleration is equal to dv dx times, in this case, the x component of the velocity vector, because the x component of the velocity vector is dx dt. So this is equal to dv dx is 5 2x. The x component of the velocity vector is 5x. And so the acceleration vector as a function of x is 25x 10x squared. So like if you have, this might be useful if you have an object that's confined to a certain path or something, okay? And you'd have to know for some reason why the velocity is going to be whatever it is at a given point on the path. But all you want to figure out, say, is the forces that are applied to this object. Like, what are the maximum forces? Like, when is it most likely to break or something? Then you could still use this to figure out where the acceleration is going to be maximum. Use that to figure out what the forces are going to be on it, even without knowing where is it going to be at 2 seconds, where is it going to be here, Let me do another example. Well, let's say this time the velocity is a function of y. So velocity is 2y negative y. We want to calculate the acceleration. The acceleration in this case is equal to the derivative of the velocity with respect to y times dy dt. And that's dv dy times the y component of the velocity, because the y component of the velocity is dy dt. And so this is 2 negative 1 times the y component of the velocity, which is negative y. And so you get negative 2y positive y. And so for a given location y, a given y position, what's the net force acting on this object? Newton's second law says F net is equal to mass times acceleration, so just multiply that by whatever the mass is, and that tells you what the net force is. Yep. Yeah. Oh, okay. Well, we're not doing partial derivatives in this class. There are areas where that is how I would write it, and then I'd need a different. But in this class, everything is a function of one independent variable, and so I'm always just going to use those subscripts as the component. Okay. Any other questions? Okay. Have a good weekend. So I won't see you till Wednesday. No school on Monday. Yeah. What? Really? Oh yeah, right. Today. I was thinking like on Monday there's school after 2 p.m. Like it's sort of a holiday, but let's not go too crazy. Yes, I won't see you guys till D form. Correct.